Hello and welcome to another episode of the Oxford MAT Livestream. My name's James and I'm joined today by current student Daisy.
Hi, I'm Daisy.
Daisy's a current computer science student who was maybe going to be on the live stream last week for the computer science episode, but we had tech issues. Daisy's here now. Any questions for Daisy in chat? Because I've seen people here are talking about UCAS applications. Kai wants to know, on a scale from 1 to 10, Daisy, how disappointed were you that James messed up with the tech issues last week?
I'll say a 6.
Oh, that's very generous of you. Okay, we do need
I wasn't too disappointed because I thought that I would mess them up. So
this is a good way of us stressing that it was me messing up last week. In between, I have found and changed one setting, and like always, when you change one setting. Alfie's got an unconditional offer from Manchester. Well done, Alfie. People are putting their UCAS applications. I saw Raphael's put something in, asked if anybody else did as well. An anonymous person would like to know, Daisy, what college are you at, and what A-levels did you do?
So I'm at Somerville. It's very close to the maths department, very close to the computer science department. You can walk on the grass. There are lots of good things about Somerville. And in terms of A-levels, I did maths, further maths, and physics.
Very nice, very nice A-level collection there. My briefing for people who are going to be guests on the live stream, my briefing is now, please don't swear, please don't divide by 0, and chat will ask you what A-levels you did. Even if you didn't do any A-levels, they'll still want to know. What's up, everyone? The issue was entirely an OBS setting, and I'm going to not go into too much detail, but I had not told my streaming software where Daisy's audio was coming from. The cable was not plugged in, the virtual cable. Oh yeah, cool. Other rules may exist. Your mileage may vary. It's live. Anything could happen. The plan for today's chat is we're going to talk about questions from the 2019 paper. I need to do a couple of polls first though, because we always start by asking how was your day today, on a scale from 1 star to 5 stars. I don't think that bar chart's going to fit on the screen. Hang on, let's do a bit of. This is a professional live stream. We can make the bar chart smaller. Does that work? That did not work at all. Okay, the bar chart's not quite visible unless people vote for one of the options quite a lot. That's not a tech issue. That's just a display issue. I will read out the votes. Daisy, how was your day today on a scale from 1 to 5?
4.
Four's pretty good. I think my day's been, 3 stars pending towards 4 stars. I'd say it's been quite an average day, but I'm currently doing a live stream, and the live stream cheers me up. People in chat are voting for 4 and 5 stars predominantly, so much so that they've shown up on the screen. As always, I'm looking out for people who vote for 1 or 2 stars. You've done a great thing by turning into a live maths session. You didn't have to do that, and here you are. So you can be proud of yourself for that one. Good. Okay, people are still voting. I'm going to let them vote. I'm kind of tracking it over time as well, to like different seasons or different like kind of time through term. How people are feeling. We're at an average of 4.1 at the moment, which is, I think, unusually good. Chat's in a good mood. Maybe you put your UCAS applications in. I know Alfie said that Alfie had a thing. Pi as a username thinks that it's a poll record possibly. Oh, and hi to Prisma as well. I think Prisma's in chat. Pretty sure Prisma's in chat. Hi Prisma if you're watching. Good, right, okay. I have another one which I want to do, which is the how are you taking part survey. Let's chat again very briefly. I did one of these before. No, that's the wrong one. Oh gosh. Yeah, no, I did it. I turned it off and on again. Right, good. That doesn't count as a tech issue either. That's just me pressing buttons badly. Me pressing buttons badly is not the same thing as a tech issue. There's sort of 3 ways to take part. You might be just doing the questions live. That one's winning the vote at the moment. You might have tried the past paper in advance if you've already had a go at 2019 papers, like I have, and like I think Daisy's tried the 2019 questions in advance, right?
Yes. Yeah.
Because we were talking before we went live. This is one of the papers that you did before you applied, right?
Yeah, this was the last past paper I had before my final one.
Right, this was the most recent one, and it was, I think from the average score, is quite a tough one, looking at the average score.
Yeah, I think I did a bit worse on this one. I was quite disheartened by it.
Okay, so Daisy disheartened, but then that 2020, the one that you did, turned out to be a little bit not like this one. But maybe people watching in chat could take that to heart as well. That this one's a bit tough, maybe. Okay. There's a couple of questions in chat that I can do, I suppose. Should I apply for Masters or Bachelors in Maths? If you're applying to Oxford, it's all the same. You just pick G100, the Maths course. We don't mind. We work it out while you're on the course. You just apply for Maths. G100, it's fine. There's only one thing you can apply for. Good. Okay. I've forgotten what I'm doing. Daisy, feel for me. What are we doing today? We're doing questions.
Well, yeah.
At some point, I'm going to give them a free vote on which math questions they want to do. But I'm aware we've got a computer scientist here live, and while Daisy's got time to do questions with us, I think we should do question 5 first, at least. Question 5 is one that everyone has to do. It's quite computer sciencey. In this case, it's written by the computer science department. We could have been doing it last week. It could have been one that Daisy was talking about last week. I think we're going to talk about it this week. I hope that's okay.
I think now they're just all going to vote for like question 3 or 4 because they'll think I'll suffer more. Is that
right? This one was a bit of a right. Okay. So if you're here for last week for recursion, you've already seen a bit of recursion. I think this falls into that category as well. How are we doing this then? So I'm writing, Daisy's talking, and I should shut up and I should let Daisy go. So what's going on in this question? What's this question about?
Okay, so this is about how we can partition a set of elements. So a set is unordered, which is an important thing to consider, and every time we take and each subset has to have at least 2 elements in it. So we've got a function here that takes a set that goes from 1 up to n, and we are splitting it into k different subsets.
Cool. I like it. I like that they say at least 2 is information. At most n is kind of a funny thing to say because there's only n elements in the set. But it's nice reminder that you can't put things in the set that aren't there. I've got a request for content. Yeah, cool. Somebody's asked about BMO in chat. I will come to BMO when I get to BMO. Okay, so we're doing K. This reminds me a little bit of a recursion question from last week where we were thinking about K as a way of splitting down the problem, but we'll get there when we get there, I suppose. They've given this nice example. They've defined the function f of n and k for n elements split into k subsets. F of 5, 2 with these 2 inputs. This first number is n, the second number is k, is 10, and here's why. Daisy, do you want to say anything about, before we get onto the parts of the question, when you looked at this past question doing revision, did you notice how they've chosen to lay out these 10 examples? It's not super important for the question, but there's something going on there that they're not listed as 2 columns of 5. There's a column of 4 and a column of 6.
Yeah, I didn't. No, I don't think I did notice that. Like when I'm looking back at it, I just.
Okay, so.
Well, I didn't really think anything of it, but it's an interesting realization that there's more that start with. If you've got them in ordered 1 to 5, then you'll have more that start with 3 than start at 2. Start with 2 elements.
Yeah. Okay. So, yeah, I suppose the order of the. It's weird, isn't it? It's quite hard to describe what they've done. It's that the order is different in the columns, but of course the order doesn't really matter for how a partition works. If you split 3 or 4 down, that's the same partition as if you listed the 3-4 bit first. So there's something going on, which is I think related to the later part of the question. When we get down to part 3, behind the scenes, and this is for people watching it at home as well, behind the scenes when we were setting this question, the examples have been laid out like that on purpose. There was some discussion about how do we lay them out. We definitely want 4 on the left and 6 on the right. So an anonymous person in chat, I don't know what, somebody says, is anyone from Black Flag? Which I think Black Flag sounds like the name of a hacking group, so that's terrifying to see in chat, but hey. Or pirates? Are they pirates? Are you pirates? Oh, it's gone. Oh no. The hacker's left. Okay, right. Good. Bye, hacker. So an anonymous person has spotted that the 5 is in a set of size 2 over here. On the right, the 5 is in a set of size 3. I don't know how quickly you could... That takes quite a while to spot, right? And there's like 100 of us working on it to spot this together. So maybe this was not the most obvious clue, but something to keep in mind perhaps that if something's been done in a slightly not obvious way, it might be might have been done in a helpful way. Who knows? I'm starting to think. Can you tell? I'm starting to think this wasn't helpful. This has helped no people. But it was an attempt.
It didn't help me. I can tell you that.
That's a very precise statement. Should we do part 1?
Yeah.
So part 1 of the question is explain why f open bracket n comma k close bracket is equal to 0 if k is bigger than n over 2. This is an explain why part of question. So we're looking for an explanation or some sort of reason to justify why something's true. How do you want to do this, Daisy? Do you want to take something from chat, or do you want to give them a clue? Or
I don't know. Let's take something from chat.
Let's take something from chat. Okay. Oh, someone says, I think I see a pattern, which is something I've learned for... Yeah, there's a pattern to them. And Rebel said, I think people are talking about the layout. There's a systematic ordering going on. And actually that's true. Within these, I think there's something going on the right-hand side as well. Within this bit. Which I can't quite put my finger on, but maybe it's like this bit goes 1, 2, 3, 4 over here. It's sort of not quite, it's not random. So 2 things in chat. Alfie's put 2k bigger than n, which I think is equivalent to k being bigger than n over 2. Yeah. And I think I know what Alfie means, but my advice to Alfie is going to be put some words on the math paper as well. Anonymous has put run out of numbers, which I think sounds like what I'm thinking of. So I'm excited by that. It's probably what Alfie's thinking of as well. And we're getting more words from more people. I'm gonna leave it open. There's a little bit of chat delay, which means that, or streaming delay or something. So we've got to leave it open for a little bit before people get a chance to type something. And also, I like that if people are typing something longer, it takes longer to type it. And I quite like it when people type longer things. Like Alfie's going first with 2k bigger than n. Respect, but then. Ooh, yeah. So some people are describing the systematic ordering on the set above, which might help later on. We're not getting any marks. We're not getting any marks by staring at this and thinking about how the system works, but maybe we're making it easier to get later marks. Running out. The theme coming through chat is that we would run out of numbers because we have to have two things in each subset. 2 things in each subset. Oh my goodness, the writing is not great. Even worse than normal. Let's go. And if we've got k subsets, then that adds up to a lot of things. Cool. I kind of stole the punchline there. Sorry, Daisy. I was planning to give you the
Yeah.
punchline. I'll give you the punchline
Yeah.
for the next bit. Sorry, over to you, Daisy. Any comment on this part of the question?
Yeah. I think the spot that each element, that each subset has to be at least 2, and then you would get that 2k. So you need 2k different elements to have. So if you can spot that, then you can see that 2k is greater than n. So that's not possible.
Sure.
We just got too many. We need more elements than we have.
People in chat are suggesting examples, which is really helpful. Or just try some examples and you'll see that it's obvious, they say, which is good advice. I think the marking is quite maybe mean-spirited to if you just check one example. So writing an example is really good, but make sure you also write something that shows that you know it generalizes to not just the case n equals 6, k equals 4. You know that it's because. If you've got that reason in there that's applicable to other cases, then that's fine with us. Okay. Next up, and I promise not to steal the punchline on this one. What's the value of f open bracket n comma 1 and y? So again, we're being asked to justify something. Over to chat and Daisy. I'm going to switch the light on.
Yeah. I think what I'd say here is just be careful. I think that's my hint here.
Sorry, I was off switching a light on. What have we got? We've got some things coming through chat as well. Chat may have frozen on screen, but I can still read it. There we go. Yeah, it's this idea that so some suggestions in chat, either maybe 1 or n. Only one way to do nothing. It's a confusing statement for me. I think there are sort of no ways to do nothing, because we're not quite counting the number of ways to do something, we're counting the number of allowable partitions, which could be 0, like in the previous part, it's 0. So if something's impossible, we're going to say 0 for the value of this function.
Yeah.
There are some cases where you would count that as 1, I think, like in a combinatorics problems.
But I think some people are saying, like, you do have to be careful with this. Like, I think when I looked back at this, I didn't do this, but there is a special case.
Yes, okay. I think there is a special case, and I remember marking, or being in charge of the marking for this question now, and yeah, lots of people missed the special case. You're being very careful. Chat, I think, hasn't said the special case yet, so chat, over to you. As a collective hive mind, Daisy says there's some special case which hasn't been identified in chat yet. Or maybe it has, I don't know. Am I keeping up with chat?
Yeah, I think someone's spotted it.
Oh, okay. Yep. The caveats. People are putting caveats in now. Cool. So some people are saying, why is it not n? N is going to be the size of that partition. I think we're all imagining the same thing, which is a subset of all of the items all together. That's the only allowable thing. Oh, I'm stealing the punchline. Daisy, do the punchline.
Okay, so we're imagining this set, which is just 1, 2, 3, all the way up to n. But if that's the only, so we've got to remember that it's a set, so the order doesn't matter. There aren't any other ways that you can pick all the numbers. So we've got to include all the numbers in there, and we've got to fit them all into one set. So there aren't really any other options available to us. So if we can make a set, then there's only one of them.
Sure. So I suppose for the people who said n in chat, the number of elements inside the set is n, but as Daisy says, that's not quite what we're being asked. The number of allowable partitions is just 1. I suppose number of allowable. Is just 1. Has chat found this special case? Yeah, what if ff11? I can see it in chat as well. I think chat agrees that except special case, like Daisy said there would be a special case, f of 1, 1, that one, if n is equal to 1, then even that partition, where you put all the elements in the set, is not allowable, because it's not big enough. So this is a sort of... I think there was 1 mark for this bonus, spotting this special case, that in general the only allowable partition is to put everything together into the set, but if n is equal to 1, then even that set is not allowed either. 1 mark, and I don't think it matters too much. I'm not very good at sharing. Sorry, I've done so many of these live streams where it's just me that I've got really bad at sharing the airwaves. Sorry, Daisy. I'm gonna get better at it. But also read out chat, because I'm a spokesperson for chat too. Because someone's put something about k bigger than n over 2, which is this is consistent with the first part.
Yeah, that's a good way of thinking about it.
You need 1 to be bigger than... Oh no, sorry. If 1 is bigger than n over 2, then the function's 0. That's true when n is 1, so the function must be 0. So by part 1, if you put n equals 1 and k equals 1, am I doing this right? Yeah. If you look at part 1 and you put k equals 1 and n equals 1, 1 is bigger than 1/2, so the function should be 0 for form 1, which is all agrees with what's been going on. There's a link between them. Is something like this always on the mat, asks chat? Not always. We do like a bit of counting. Systematic, what was Rebel's phrase? Systematic ordering. Which is a good catch-all term for all of these together. Part 3 is the really hard part, because this is where we're going to set up a recursion relation. Daisy, do you want to say, as a computer scientist, reading this part of the question, how do you read it? What does it mean to you? How do you take in all of this information?
Okay, so I think I would break this down. So I think these are, at least on the surface, these seems like very mutually exclusive cases. So if we count 1 and then count the next one, we can just add them. At least that's what it seems at first. And you'll have to check that, but it'd be a bit mean if they weren't.
Right. The question's trying to help us, I suppose.
Yeah. So the first part, what I'd think about how. So you've got to think about how many ways you can do this related to some previous value or values of f. So to think about what values of f we might be calling, well, if we're making a new pair, then that's an extra partition. So it's going to be in terms of k minus of f something k minus 1, and we're taking one element away, so it's going to be, and we're taking 2 elements away, sorry, because we're taking the n plus 1's element away, and we're taking one we're pairing it with away. So we've only got n minus 1 elements left, and we've got k minus 1 elements left. So it's going to be, I think it's going to be something to do with that.
Right. Something to do with f of n minus 1, k minus 1, because you're thinking about the other leftover bits of those splitting up. You've still got some partitioning to do, n minus 1 things to split into k minus 1 subsets. Okay, but you've said it's something to do with that. I like that. The sort of you're trying to do. I really like the phrase previous values. We could argue about sequences and how this is sort of a 2D sort of weird sequence and is z squared the same size as z. But the previous values is a really good way of thinking about what these things are. I've interrupted you, sorry, because you were about to tell me that it's something to do with that. But maybe refine that. I don't know. Up to you.
So now we've just got to think about how many ways we compare, how many different ways we compare n plus 1 with another element that's left. And then I think you could just, and then that would be how many times you have to multiply fn minus 1 by.
Right, okay. So this is like last week we had a lot of multiplication and separately adding for mutually exclusive things being added and independent choices being multiplied. You've said how many things it is, and I've got to really concentrate for how many other elements are there? Is it n other elements?
So yeah.
Yeah, okay, right, okay. I'm going to start writing down a formula. I don't know. I just want to keep track of. We're talking about this thing where we've got n plus 1 elements, splitting them into k subsets. And our first mutually exclusive thing, so there's going to be a big plus sign in here, but our first mutually exclusive thing is to maybe first choose another element. So you've told me that's n ways for pairing it?
Yeah.
And then you want to multiply that by, oh my goodness, that looks nothing like an n. And then multiply that by, what was this one?
Oh, so it would be n minus 1, k minus 1.
Right, because that's dealing with all of the rest of the elements. We've got n minus 1 of them, and we're going to put them into k minus 1 subsets, because we've already dealt with the subset, and now we got, okay, good. Cool, okay, with you so far, that's how many in this first bullet point case, I think, tick.
And so this other case, so we're taking an allowable partition of 1 up to n and then adding this final element to one of the subsets that already exists. So, I mean, the first thing that I just noticed is that this is making a subset of size 3 or more. So we're putting this last element into a subset that's greater than or equal to 3. And then, but in the previous part, we were doing one that's equal to 2. So these are definitely separate cases, which was a concern I had, but we don't have to worry about that anymore. So now we've just got to think that, well, we're taking a partition of just 1 up to n, and we're using a partition that already exists, so there are still going to be k subsets. So it's going to be in terms of f, n, k.
Cool. So this one's something to do with f, n, k. So you're thinking about taking that collection of existing subsets. We're not making any new subsets, so probably it had k subsets before, and we're adding something in. There are k choices for which one we add it to, right?
Yeah. I think so.
Lay down or up? Ooh, we may have just lost some stream quality or the internet or something, but we're going to carry on because that's just how the show works. Okay. So in this case, it would be k times f of n k. K because we've got to choose which subset to put it in. F of nk because we need to choose f of nk because we need to choose a previous set of k subsets with n things in, and then stick the n+1 into there. Questions in chat. So we're going to go back and explain a couple of bits again. First one is, why are we multiplying? Daisy, do you want to take that one? Why? I think back here for the multiplying by n, why are we multiplying that?
Okay, so when we're pairing n+1 with one other element, so this stuff, so it could have we could have like the last element paired with 1, or the last element paired with 2, or 3, or 4, or 5, or all the way up to n. And all of these are going to be separate cases. So you're going to end up with a different partition depending on... So we have to multiply, otherwise we'd be under counting.
Yeah, up here, so I think perhaps it's helpful for us to note that f of 4 comma... What do I want to say? I want to point at the diagram above, the listing up here. So the split here is the two different bullet points. Let's see if we can get this going. On the left, the element n+1, the biggest element, has been paired up into a set of size 2. But there's not just one possibility for what it's been paired with. There are 4 possibilities for what it's been paired with. And in each of those cases, you can't really see it happening here, but in each of those cases, we got to worry about the ways to partition up the remaining stuff. So you've got to play all these games with the remaining 3 elements. There's actually only one way to partition 3 elements, because your subsets have to be size 2. So there's only one way to do it. But this here, f of 3, 1. What do I mean? There's only f of 3, 1 is 1. There's only one way to partition that up. Those 3 elements into one set. But overall, there's 4 different possibilities of what we pair the 5 with. The preamble is a hint, sort of helpful. When it says add n+1, it means adding in the element n+1. Sorry, yeah, this bit, maybe it could have been clearer. Adding the number n+1 is going to be a disaster, because if you add the number n+1 to one of these numbers, then you'll get a number that's too big. So we need to add the element. Maybe that could have had brackets around it or something. Okay, so you're going to multiply because there's lots of different cases for what we pair the 5 with. This n is like choosing what do you pair the 5 with, and then in each of those cases, once you paired it with something, you've got to do some partitioning on the rest of the stuff. Now, there might only be one thing, might only be one way to partition the other stuff. F of 3, 1 is just one thing. That might be quite a lot. The 2 bullet points are separate cases, says Kai, and you add them. For the first one, you choose n different elements to pair n+1 with, and then you have some ways to deal with the rest, because you've only got that many partitions. Kai's comment is, I think, a really good description of this structure in the first term. It's got a question mark on the end, which I don't understand. Kai, I agree with Kai. Good. Anything else to say about the second term? Do you want to explain the second term a little bit more, just in case people want to hear about the second term again?
Okay, so we're taking an allowable partition of 1 up to n. So it's going to be, so the first argument is going to be of this function is going to be n, and we're not adding any. When we're using the partitions we've already got to make this new partition, so we're not changing the number of partitions. So it's going to be in terms of f, n, k. It's going to be something to do with that. But now we've just got to think, how many ways can we add n+1 to one of the existing subsets? Well, because it's in terms of f, n, k, there are k different partitions. So we just have to multiply that by k to get to count how many we have.
Yeah. Which one are you going to put the 5 into? Let's see if I can point at this on the preamble diagram. Point at what's going on. I'm going to use a different colour for circling things, because I've got a lot of dark blue going on. These ones, these are the partition. These are made by the allowed partition. Oh my goodness, that 2 is awful. 1, 2, 3 paired with 4. Take that allowable partition of 4 elements into 2 partitions and just shove the 5 into either the first bit or shove the 5 into the other bit. And then these next two are made by taking a different allowable partition of 4 things into 2 sets, 1, 3, 2, 4. And adding the 5 into one of those, and then the last two you can see are the other partition of 4 things into 2 sets, stuffing in 5 things as well. Stuffing 5 into either the 1, 4 subset or the 2, 3 subset. So it's kind of where these have come from. That within the column they're also listed in a logical order, but they kind of turn up in these pairs. So this is kind of on the left 4 times 1, and on the right 2 times 3. Right, okay. One of those times I concentrated way too hard to say a true statement about the number 6. Good. This holds. I think this holds for all k and n. I wouldn't worry too much about checking that. I mean, it holds like this, so that the things actually exist. I suppose. Don't really understand where we've used that inequality or why we need that inequality around. Any ideas, Daisy? Why has it got this two?
Oh well, if k were 1, then we'd have we'd be partitioning it into 0 things, which.
Oh, okay, right.
Which is a problem.
This term is nonsense. This term in the middle is nonsense if k is equal to 1. So we're only talking about k bigger than or equal to 2. It's sort of implicit. As soon as we write this down, we're only thinking about k being bigger than or equal to 2. Okay.
And if k is equal to n, then
does anything go wrong if k is equal to n? I don't think anything goes wrong. I think it's true for these ones, but maybe also true for some other values of k and n that are less interesting. Anyway. Might have got distracted. Yeah, I guess we've already done the case. When k is equal to 1 and k is equal to n, we've already done those ones at the top. Yeah. Those are parts 1 and 2. There is now a long and boring calculation for working out the value of f7, 3 that I think we should skip for time.
Yeah.
Yeah, I'm not keen to turn the handle on this. The way it would work, so that people watching chat are on board, that we'd work out f7, 3 is equal to. We would use this formula, plugging in n is equal to 6, k is equal to 3, 6 not 7, so that we get a 7 over here. So it'd be like 6 times f of 5, 2, which we know from the preamble of the question. What a helpful question. And 3 times f of 6, 3. This is what Daisy called previous values of f, and then we keep working down and hope that eventually we get down to stuff we know about.
Yeah.
Those different stuff.
So I think if we were to do this in the exam, I would write it out in a table, and I'd start with like really basic values like n equals k, and then build up from there, and then we can just fill up the table until we get to f of 7, 3.
That is a good strat as well, to work upwards from small easy cases and hope that you get to 7, 3 eventually, or work downwards. I think looked at both. For an easier problem, we looked at both strategies last week. And because it was an easier problem, nobody really, I think, liked the idea that we were doing it in 2 different ways. Just for an anonymous person in chat, you can add the n+1 in all the different subsets. There are k different subsets. So I think we agree you can put it in all the different subsets. There are k of them. That's k possibilities. I don't think you need to multiply by n. Remember that once you're in a subset, the order within that subset doesn't matter. So just choosing which subset to put it in is enough. And there are k choices. We did it. Which subset do you want to put it in? Left one here or the right one over there? Good. There are then some possibilities. F6.3 is interesting because it's related to the last part of the question, which I do want to talk about. I kind of want Daisy to talk about the last part of the question, if that's all right. obviously we can talk about how to do this part of this question. Give a formula for f of 2n n. It's the last part of the question. It looks a bit different. Well, what do you think, I suppose, when you see this sort of part at the end?
This little part at the end, the final part.
Yeah. I'm trying to skip I'm just trying to skip the 7-3 calculation.
Okay.
Because I don't feel like writing out any more lines of this. We get down to some numbers at the end.
Yeah. Okay. So when I looked at this, I just thought this does not look very nice. So I think that the easiest way I might think about this is to kind of go back to basics and not use the previous parts, because it doesn't look like a very nice thing. But we can try it both ways, I think.
Doesn't look nice. Looks different. My heart kind of sinks a little bit because it looks like a lot of work. We already did a lot of work to very carefully understand this recursion relation. It's not obvious that our lovely recursion relation is going to help us with this last part. We might have to do some original thinking.
Yeah.
We've got one fan though in chat who gets a shout out because they've put the username as Lewis Hamiltonian, which is a very good overlap of things I like. If you know about mathematical induction, Kai is suggesting we use mathematical induction. If you know about it, then go for it. I think not everybody here knows about mathematical induction. It's not on the math syllabus. So Daisy and I are going to try and do this question without using mathematical induction.
Yeah.
Do you think you would try using the recursion relation? I've done that really hypothetical, but you say you've done this past paper question.
Yeah, I don't think I would in a paper, but we can try it.
It's weird.
It might be possible.
It might be possible. Something I suppose I can sort of see is that if this is about even numbers over here. If this thing is even, then this n minus 1 is also even. But I'm a bit scared because
I think what I'd hope is that one of these terms might disappear, and then we just got like a recursion in terms of 1.
That would be nice. Not obvious to me that it's going to be that good. I'm worried that this thing will be odd, so it won't be one of the ones that we're interested in. And these are good, but then that's not be 2n minus 1. Oh, is this maybe this is 0 because it's too big? Maybe this is good. Maybe this is good. Okay. Oh, there's a bump from Irvin. How much detail is needed to get full points pot 3? Enough so that the golden rule is enough detail that we know that you're not bluffing, which is not very much, but enough that we know you're not bluffing. So saying something in words, preferably, to explain why the first part is something like this, and why the second part is something like that. This is not actually a show that question, so you get, I think, at least one of the marks for just getting the right answer down the end, which is good. Easier to mark. Suggestion from Kai to try easy values of n. An anonymous person has backed up my vague suggestion that annoying term might vanish. And some sort of maybe factorization. Okay, maybe that works.
Yeah.
But Daisy, you said you wouldn't do it like this. we've done about.
So I think another way we could just do it is like to think about how many ways we could. So when we've got f2n n, then we know that we can spot that means that each subset is a pair. Like we can't have it smaller than 2, but we can't have a subset smaller than 2. That's not allowed. But if we've got one bigger than 2, then that would mean that one of our subsets has to be less than size 2, which is also not allowed. So we've got to count how many ways we can pair them.
In my kind of overly flowery language, I would say that this is on the cusp of being possible. This is only just possible that you can partition 2n things into n allowable partitions. We proved earlier that if the first number is more than twice the second number inside the brackets, if the first number is more than twice the second number, it's impossible. So this is right on the edge of being possible, which I think is why the recursion relations simplifies, because it's near the edge of the bit where there's loads of zeros. So it's nice and simple. But we just got to stick maybe putting these two n things into pairs, which I don't know about you, Daisy, that's a problem I've heard before, because it's the tennis tournament problem. No, it's like a version of the tennis problem. Have you heard this? Do you know what I mean?
No, I haven't heard it, no.
Okay, so...
I mean, I might have done and then forgotten about it.
When you're about to start a tennis competition, you've got an even number of people, and you need to pair them up to play tennis against each other. That's what we're doing here, by the way. We're taking an even number of things and we're pairing them all up so that they can play tennis against each other or something, I don't know. And it doesn't really matter like who's on the court first for my tennis tournament.
Yeah.
I mean, I don't know. It doesn't really matter who's on first, so the order of those things doesn't matter. And it doesn't matter which way round they are in the pairs, because yes, one of them stands at one end of the pitch. It doesn't make any difference. The pitch is fair. So it's just how many ways can I split these two n people into n tennis matches? Which is a problem I think I'd seen before, so I know the answer to this. I think, but more importantly than that, I sort of vaguely remember the reasoning for this. It's not the only tennis combinatorics puzzle I know. We could do a tennis episode at some point. Let's not do a tennis episode. That sounds rubbish. So do you want to? Okay, so we've got two strategies on the table. One is to use the recurrence relation, and maybe it simplifies nicely and does something to do with n factorial. Or maybe we think about just partitioning into pairs, which I think is Daisy's preferred method. So I think I'm going to hand over to Daisy. How do we do this partitioning method? Is that right?
Yeah. So okay. So basically we just have to count how many ways we can pair these up. So I think one way to look at it was we'd see if these were like ordered pairs. So if the order mattered, I think we could count it quite easily, because we could just line them up and then split them into pairs. And then we just how much we're overcounting by. I think that would be it's quite an annoying way to do it. It's not very satisfying, but I think that would be the easiest method here, would be to just consider what would happen if the order really mattered, and then divide to get rid of that problem. So
this is a counting strategy. Sorry to interrupt. This is a counting strategy I've seen professionals use that maybe people aspiring to be professionals could really learn from. This method of overcounting, but then allowing for the fact that you overcounted. I think I hadn't really, as a kid when you're learning to count stuff, nobody tells you this, like, it's cool if you count everything twice, that's fine. As long as you count everything twice. No one's like...
Yeah. It comes up a lot in the computer science course. You have to get used to it.
Right, yeah. There's like strategic overcounting, but overcounting in a very fair way. So you keep track of, you've done a certain amount of overcounting. So your first line, the first thing you wanted to do there, I'm going to see if I could draw a picture or something. You want to line up, did you say, I don't want to put words into your mouth, sorry. What's the first thing we do?
So I think just consider all the numbers 1 up to 2n.
Okay.
So now we could imagine if we were, so we could try and pair them in a way where, so if we just considered how many ways we could order these, that's 2n factorial ways.
Okay. So we could shuffle them all up, list out the 2n things. There are a factorial way of doing that. And I guess is the idea then that you're pairing the first thing with the second thing, the third thing with the fourth thing.
Yeah.
I'm trying to draw a sort of framework for you to put the things in.
Yeah.
Like a sort of, but it looks like I'm just drawing faces or something, or elephants. This is like the structure of where you would put the things. You put the things where the dots are. I've got your sets ready for you, with all the commas and the curly braces. But you're gonna put them into these gaps, which if you just take your row of 2n things, shuffle them and put them into the gaps, that's overcounted a bit.
Yeah.
Daisy's going to explain how much overcounting that was.
So the first thing we've got to consider is that in each pair, we can have them in either order, and it's still the same subset. So that's just for every set, we're overcounting twice. We're just counting it twice. But because we've got n different sets, and we're multiplying how many there are together, that's like 2 times. We've got 2 to the n. We're overcounting by a factor of 2 to the n.
Yeah, it's a lot of
And
overcounting. It's like a lot of little binary switches, if you like binary, or if you like switches. This shuffle order drops the pairs down, but then the pairs could appear in either order. So each pair could be one of those orders.
And then the other way that we are overcounting is that the pairs are still ordered, but obviously we don't care what order the pairs are in. And so there are n pairs. So we've got to so the n pairs. So there are n factorial ways we could order them. So we've just got to divide by n factorial.
Okay, order of pairs for what's going on. So we need to divide by a factor of n factorial to allow for encountering these pairs in a weird order. Right, cool. Okay, so advanced counting and overcounting and dividing strategy. I love it whenever I see it. Daisy's answer is 2n factorial, I suppose. Divided by, divided by 2 to the n factorial. Okay, cool. People in chat are really confused, but that's all right. we're gonna get there, chat. Don't worry. And we are going to do other questions as well. So let's just quickly remember what partitions are. If you've just joined the stream, we're counting partitions, which means splitting down a set of things into subsets. The order inside a subset doesn't matter, and the order of the subsets doesn't matter. The partition is just how the things are grouped up with each other. It's a bit like if you, I don't know, if you have to split items out into different categories or something, you've got to match things together. Then partitioning them up is like splitting them up into these different groups. For this question, all of our partitions have to have, all of our subsets have to have at least 2 things in, but the order doesn't matter inside there, and the order of the subsets doesn't matter. So here are the 10 partitions, where the one with 5 and 1 the other way around over here doesn't count as a different partition, and the one where the 1, 5 subset was listed afterwards doesn't count as a different partition. So these are all of the allowable partitions up there. And Daisy's just done an argument for how many there are if you've got twice as many elements as subsets. You've just got pairs, by thinking about shuffling all the items, chucking them down, and then allowing for those rules about actually some of these count as the same partition. So that's pretty good. Okay. There is a recursion relation way to do this. Daisy, help me out. Can you see, is it worth doing on the screen or is it really horrible? That's a hard question, sorry.
I don't like it, but it's.
Oh, is it?
I
It's
think
not.
that it's not something I would like. That's what I'll say. I wouldn't want to do it in an exam.
Yeah.
That's what I think it's going to end up being like.
I think this is a little bit hard to write out actually, because people are not going to like this in chat, I can tell. So I'm trying to write out the recursion relation in this box up here. Oh, solid gold from part 3 or something. People are not going to like this. I'm trying to write it out for the case 2n. So I'm replacing the n plus 1s with 2n. Ugh, what does that even mean?
Yeah. So yeah, that has to be like a 2n minus 1 there, because
really this is describing, the n's and the k's don't really matter. It's describing how you subtract 2 from the first argument and you subtract 1 from the second argument. But that's a bit of an abstract way to think about it, I suppose. So this thing here is 1 less than the thing you had on the left. For me, the thing I had on the left was 2n, and this k over here, so you write down the same thing over here. So then, chat's really not going to like this. You know, so I'm trying to take the thing in the box and just copy it out.
I think we need a 2n minus 1 at the start there, as a factor.
Oh yeah, true. Thanks. Did people in chat call that as well? Yeah, you're right. It is a 2n minus 1.
I think there's something nice. Yeah.
I'm not replacing. Gosh, I'm not replacing n with 2n. I'm replacing n plus 1 on the left with 2n, which means that I should have two-stepped it. You're right. Subtract 1 from all the n's and then replace all the n's with 2n's. Yeah, okay. That is a 2n minus 1. Brilliantly, this term is 0. This is 0 by part 2. The first number is too big for the second number. You can't split 2n minus 1 things into n partitions of size 2 or more. So this is 0, which gives us this lovely relationship that f of 2n comma n is equal to odd number here multiplied by the previous value of this function. So that's actually really nice. It's just you end up with the product of the odd numbers.
Yeah.
Product of the odd numbers is quite hard to write down, but you get an odd number and then you'll get the previous odd number and you'll get all the odd numbers together. Homework problem, I suppose, chat. The product of the odd numbers is equal to this thing that Daisy wrote down with all of these 2's and n factorials and 2n factorials. I have that in the camp of not obvious, but does make sense when you try writing them both out. Right, okay. How are we meant to do this in the exam if it takes our whole live stream nearly an hour to do it? That's a valid question. Daisy, do you have any questions before I do that particular question? Do you have any advice about time management?
Not really. I think I didn't have much advice. I think all I would say is try and do some past papers in practice, timed, and also this is more of a psychological thing, but try to order them in a certain way. I think I personally found that this is a personal thing, but I think I did some multiple choice last.
Ooh.
Because that just changed the pressure for me, psychologically.
Oh, that's interesting. Multiple choice last. There's a hot tip. My advice for this particular question, how are you meant to do this exam, it takes nearly a whole live stream, nearly an hour to do it, is while you're doing the exam, do not try to answer the question. Do not try to explain the question to 100 other people at the same time. That's my main advice. You'll find it goes much faster if you don't also have to explain it to a live stream at the same time. We did go backwards and forwards a little bit, but that's my jokey advice. We're going into more detail. We spent a lot of time talking out loud about different ways to think about these numbers, when really in the actual exam, under the rush of time pressure, you might just read through it and get going. You might get to answering question 1 immediately, with part 1 immediately without having as much chat as we do. Less chatting in the exam, right? Redfear, I would prefer it if you use the available space in the booklet first, because we're going to scan them electronically, and the scanning machine is expecting a certain number of pages. It's not a disaster if you use bonus paper really, but it makes our life slightly harder. How much working out space do you get? I think it's this much. Did I improve it for this? No, I improved it. It's not this much. You now get each long question is separated. They're on multiples of 4. So you get, the question takes up some space, but you get kind of 4 pages including the question. Okay. we did spend a long time on question 5, but I think it was worth it because I think we went really into detail on the recursion bit, which people find very difficult, and people did find very difficult. At least one person didn't get it, and then we talked a bit more and then they did get it, which is what I'm looking for. Thank you, Daisy. Do you have to go, or do you want to do another computer science question?
Yeah, I don't mind doing any questions.
Didn't hear what you said,
I want a
sorry.
challenge. I want a challenge, so any question.
Any question? Okay, I'll take
Yes.
that challenge. Right, yeah, okay, let's mix it up. We have a what next survey. Okay, if you're watching in chat, we're 1 hour in, don't forget to drink water, stay hydrated. And we're also going to vote. One person's voted straight in on the computer science question. If you'd like to see what we're voting for, you can get the test paper. I think it's linked in the YouTube description. It's also linked in the Slido sidebar, the slide bar, if you will. You can find out more. You can vote for multiple questions down there. We're going to do whichever one people really want to do. Oh, votes for computer science. People want to see Daisy do computer science questions. If we do another computer science question, we will obviously, if we do anything, we'll do it faster. We will go faster for the next one so that we do more than 2 long questions. In 2 hours. This live stream used to be 1 hour.
I don't remember it being 1 hour.
Oh,
I
in
thought
2020 it
the
was 2 hours, but it was a bit weird.
Oh, okay.
If you saw the show, did you see the show in 2020?
Yeah, I went to a few of them.
The show was really weird in 2020. It was mostly me sitting in silence while people did the questions live. I was very strict about it. It was like you come to this live stream and you do the questions live, and I sit in silence. Whereas now it's got a bit interactive. 2021, last year, in between, we tried doing it with James talking all the time, no silence, but only 1 hour. That was a disaster in a sense because we didn't get through very many questions. Here we are. Yeah, who's voting for question 5? Question 5, how's that doing in the poll? Not amazing, I would say. Yeah, okay, good. Maybe I should go through and remove the ones we've done. That just feels too... People vote for it is because they want to see it again, right? Question 2 is doing quite well in the poll, and question 2 is a question that everybody has to do. I think we're going to talk about question 2. I'm going to leave the vote running just a little bit, but it's pulling ahead. I'm going to try and find question 2. Daisy, I think chat's been nice to you because question 2 is one that you would have had to do as a computer science applicant, and presumably it's one that you thought about doing. I remember this question.
Yeah, I don't remember it.
You don't remember this question? Brilliant. Okay, so we've got one person who remembers the question, one person who doesn't remember the question, and a live stream chat full of people who would like to see the question, but only 30% of them. But that's okay. There are no votes for question 1B, which is interesting. In interviews, do you get... let's do this interview chat very quickly. Sorry, I only ask maths questions in maths interviews. I'm only interested in talking about mathematics. During the live streams, I chat about everything, but in interviews, I haven't got very long, so we just talk about maths questions for me. Okay, I'm stalling for time a little bit so that Daisy has a chance to read the question. You all right there?
Yeah.
You said any question. Here we are. Okay, and we're going to try and do this one a little bit faster than we did question 5. You ready? Oh, I think I've lost Daisy. Have I lost Daisy? No. Oh, I think I've lost Daisy. And maybe I've lost the internet. Is it me? Okay. I'm going to start talking about question 2 because I think I've still got the internet. We will see if I've lost the internet. And in a second we're going to see if we get Daisy back as well. Okay. Question 2 wants us to multiply out all these terms so that we get... Oh, Daisy's back. Hi Daisy, lost you for a moment. I'm just doing part 1.
Oh, so
you alright?
I didn't lose you.
Okay.
Yeah.
I was terrified it was my internet. We're going to multiply out all these terms. On the right, n is the degree of the polynomial. Remember the polynomial session, everyone? We talked about this. There's the biggest power of x. So the biggest power of x comes when I take the biggest powers of x on the left-hand side, which comes when I take this x to the 1, x to the 2, and x to the 3. I'll take the x cubed from that bracket. I'll be really greedy about it and just pick up all the biggest powers of x that I can see, and I'll get this sum, 1 plus 2 plus ... plus k. I know this sum. It is the sum of the whole numbers. Is Gauss in chat? Oh no, Gauss can't be here today. So k plus 1 over 2. There is a fun story about Gauss doing this sum while aged 5. Kai's very nice. Look, Kai's telling me that Kai can still hear me. That's great behaviour, thank you. Cool. Daisy, how do you feel when you see by doing blah or otherwise? Do you feel like a kind of rule follower, or are you more of a rebel?
So I'm usually a rule follower, as long as I've read it properly.
Right.
Like, I did that on my mat, but it wasn't even an or otherwise. I just did it differently.
Ooh. Okay, we do.
I think that lost me marks.
It is very tricky to mark it when someone's actually rule breaking. Let's not get sidetracked. I would almost always do it with the method they're saying. I think that's what Daisy said as well. Unless if there was something really obvious to me that worked as an otherwise, and I'd already thought of it while reading the question, then I might go for it. But I'm just like 99% gonna set x equals 1. If I do that, then on the left I get 1 in every bracket, so I get 2 to the k, and on the right I get the sum of the coefficients. Okay. Daisy, your internet's back. You have the option at any stage of pretending that it's gone again. What's the link between this sum of the coefficients and this fact about A max?
Okay, so this sum. So if we consider this sum, so if all these coefficients were equal, then it would be equal to n plus 1 times A max.
N plus 1 because there are n plus 1 of them, weirdly, because there's a 0. This is a sequence that starts at 0. Let's not get into that again, chat. There are n plus 1 of them, and if they were all equal, sure, they would all be A max.
And if they weren't all equal, then at least one of them is smaller than A.
Yeah, so I guess less than or equal to. So they might all be the same, or some of them might be smaller than the maximum. None of them are bigger than the maximum, so each one of these is smaller than or equal to the maximum. That's something you can say about anything, I suppose. You're smaller than or equal to the maximum. Good. So that's this, and then that just rearranges really nicely to the expression here. Here I think the key thing was to not panic when this A max turns up on the left. It's a new thing that needs a definition, and the definition is hiding down here underneath. But we should not panic because there's a definition here which really helps us out. We need this definition in order to do anything at all. I've lost Daisy again, but last time Daisy came back in a second. Okay. Someone's asked which college Daisy is at. Daisy is at Somerville College. Daisy's just dropped off. We're going to quickly switch to this one, and I'll switch back when I get Daisy back. Trapezium rule is no longer on the MAT syllabus. Okay, I've lost Daisy. Here are the tech issues. 1 hour in. Okay. Part 3 wants us to fix I. So this is a little bit confusing, perhaps. We want to fix I and explain why eventually. This eventually is kind of eventually as k increases. This thing eventually, AI eventually is constant. The increase in k eventually has no effect on AI. Daisy's back. Hi, Daisy.
Hi. So I think for this one, so I think so if we've got say this x to the, so as k increases, I think like when we're adding more, so as k increases, we'll just be adding more things we can multiply by. So that'd be like times 1 plus x to k plus 1, x to k plus 2. But these are too big to be included in x to the I. So as soon as k is bigger than I, then it's not going to make a difference, because we can only choose to multiply by 1. We can't choose to multiply it by x to the k.
Love it. Yeah, if k is bigger than I, then the new terms, I'm going to call them new terms in pkx, don't affect. Oops. Don't affect AI. Oh my goodness, the handwriting, it's gone. Handwriting's disconnected. What college am I at? I'm at a new college. I do some teaching for new college at the moment. That's a that's a sort of gig economy, short contract sort of thing. The integral of 2 to the x is not on the MAT syllabus. We talked about it on one of the live streams, but I think I explained in the live stream why I think it's a bit too complicated for a to be assumed knowledge for the MAT. I think you can do it. I think you can do it with, if you really concentrate on logarithm and exponentials and rules for differentiating e to the kx. I think you can do it, but it's hard enough based on things that you know that I probably wouldn't assume. Yeah, what does constant mean? We argued about this a lot when we were setting the question. It means constant as a function of k. It's not very clear, is it? So these AI, secretly they also depend on k, because these are just the coefficients in pk. So really these AI also depend on k, because for different polynomials you get different constants. That's a bit unfortunate. So it means it's trying to evoke the idea that k is a variable that's changing, but AI is sort of changing for different values of k. Explain that again, please, says an anonymous person in chat. The key thing to understand is what happens when we change k. Daisy explained it. When we change k, if I make k just a little bit bigger, maybe it was 10, now I'm making it 11, that means multiplying by 1 plus x to the 11. And then when I make k 12, that means multiply by another term in this dot's hiding a lot. When k is 12, it means multiply by 1 plus x to the 12, and keep going. And if I keep going, then eventually this x to the 12, x to the 13, it doesn't really matter if I'm just interested in the coefficient of x to the 3. If I'm just interested in the x to the 3, then these massive powers of x have no effect on the x cubed coefficient, because I have to ignore them, otherwise when I'm multiplying out, the thing will be way too big a power of x. So all these, after a while, these terms are just inconsequential for my, for a big enough term, small enough coefficient that I'm interested in, there's this trade-off. Which is why we've said that if k is bigger than I, then these new terms don't affect that coefficient. The 1 is good. The 1 means that the term stays there, but the plus, who cares? Massive thing. Massive power. An anonymous person says they're applying to New College. If you're shortlisted, I will not be your interviewer because I'm not interviewing for New College. But if you get in, I might be teaching you. Okay, next part of the question. Oh, I've taken over a bit. How's it going, Daisy? You alright?
Yeah. Okay.
I did the rerun. I think you explained it very well, and then I kind of said what you said again.
Yeah.
I love it when there's a student in these questions. This kind of person who is correct, person who's wrong. I've seen TMUA do that quite a lot, where they've got this student like a proof that's wrong. Here, we're told that the student has correctly calculated for k equals 6, that P6 is this. Behind the scenes, fun fact, the word correctly was added in a later draft, because later on in this question you're going to seriously doubt the abilities of this student. So we needed to tell you that they're actually right about this bit. We needed to reassure you the student has successfully worked out P6. Okay, first off though, they're going to guess that AI is equal to AN minus I. They've spotted... Do you want to interpret this in words, Daisy?
So, I guess what we'd be saying is that the coefficient of x to the of x to the I is equal to the coefficient of x to the n minus I.
Which like is how these threes match up. The coefficient of x to 5 is the same thing as the coefficient of x to 16, for example, and also reading kind of inwards. So that's what they've spotted. This is in fact correct. You prove it by substituting in 1 over x for x. So you work out that 1 plus 1 over x. Oh gosh, this is going to be a bit slow to write. I think I'm going to explain how this works, but not actually do all of the writing out. It's another part where it says by doing blah or otherwise, and I think both the people on the live stream are in favour of just do it the way they suggest. Oh my goodness, I'm plugging in 1 over x, but it's a bit painful. Am I going off the page as well? There we go. My handwriting's really not good today. Okay, and so on. If you then multiply both sides by x to the n, then you get out exactly the thing that you want. On the left, after you've multiplied by x to the n, that thing on the left turns into the original polynomial. We know its coefficients. And the thing on the right turns into the polynomial with the coefficients written backwards. So it's a nice proof. Compare coefficients. Yeah, this is in words what Adrian said. The coefficients are symmetrical, like that. You prove it by substituting and then just doing a couple of operations to multiply up by a big power of x and to compare coefficients. Okay. Not able to understand the whole question, so someone in chat. What lines did the student make a mistake type of question was what I was thinking about. Yeah, that's what I was thinking about for other things as well. Sorry, catching my chat. How's chat doing? Chat's doing well. Okay. On the basis of the same calculation, last part of the question, the student guesses that all whole numbers in the range 1 up to a max, so for here in their example, a max is 5, the biggest coefficient, 1, 2, 3, 4 and 5 all appear, 1, 2, 3, 4, 5 all appear among these coefficients for all positive integers k. And the question all knits back together again and says use part 2 to show that in this case the student's guess is wrong. Justify your answer. There's part 2 at the top of the screen. I feel like we should do strategy advice before we start explaining why this student's wrong. It's not quite a line where the student's wrong, I suppose it's just their guess is just sadly incorrect in general. This is the first bit we've seen today where it says using part number. Do you have any? Is there anything we should say about that? I don't know. Over to Daisy. Anything you want to? Anything to say about that in general?
So I guess we can think about how we could have these. So one way I guess is that a max could just be equal to. I guess on one extreme end we've got a max is just equal to 1. So then we just have all the coefficients are 1. And then on the other extreme end, we could just be that we have 1, 2, 3, 4, counting all the way up to a max with no repetitions. So I think we've got two like extreme cases there that we've got to think about.
Yeah. Okay, so if the student's right, we've got to have all of the numbers appearing, which looks like it does happen. It does genuinely happen in the case k equals 6.
And we know that this a max is at so we know that this so from part 2 we know that a max is at least 2 to the k over n plus 1.
Yeah, how I read it, I suppose, is that this says that a max is big.
Yeah.
Okay, so there's detail. We've worked out this detailed thing about how big it is, but the inequality being this way around, and I think I have to do inequalities in words in my head. I'm just not mechanically, like, I don't know, analytic enough to do inequalities mathematically. I have to do them in words. This says that a max is big, and because we're trying to prove that something doesn't happen, I guess part of my brain is already thinking a max is too big. That's kind of what our proof is going to be like, right? A max is big, that's part 2, and the story is going to be, I think, a max is too big for all of the coefficients to appear. And so I've kind of worked out what it must be, what the logic must be. I haven't really filled in the details. What does it mean to be too big for all the coefficients to appear? But I can try. I feel like that's the structure of what we're about to say. And someone in chat has said exponentials grow faster than linear, which is, I think, the missing piece of puzzle for what's going on. I'm going to let Daisy have a go at explaining that, I think. Sorry to put you on the spot. Here we go.
Okay, so...
So the student believes that every number appears. The structure I'm imagining is that's not going to happen because there are too many coefficients, too many numbers between a max and not enough coefficients. So a good idea would be to think about how many coefficients are there.
There were n plus 1 coefficients. So to count up, then a max have to be less than we could do n plus 1.
Yeah. n plus 1 things that could be different. In fact, half of them are the same as the other half, but let's not worry about that right now. Even if they were all different, there's only n plus 1 of them. So I'm already putting in these words like only and too many because I kind of know which way around it's going to go. So I'm trying to imagine it for myself. Right, only n plus 1 coefficients. Loads of coefficients for large. Loads of coefficients, but I've got to imagine that it's only n plus 1 coefficients. And it makes it absolutely huge. It is bigger than or equal to 2 to the k over n plus 1.
So we've got that n plus 1 is greater than 2 to the k over n plus 1.
Yeah, and so we would need, I'm going to multiply that up a bit, we would need that n plus 1 squared is bigger than or equal to 2 to the k. But if k equals 100 or something, we know that n is 5050. N plus 1 squared is less than 2 to the k. I say that's semi obvious at that stage. That 2 to the 100 is absolutely massive. 5051 squared is not that big. I could work out how big 2 to the 100 is if I really wanted to. Or I suppose the thing people are saying is that exponentials grow much faster than polynomials. The left-hand side there, n plus 1 squared, is a polynomial. It's 4th degree polynomial in k, and the right-hand side is an exponential. Oh, good stuff. Jack, still always just here for the water bottle, which is how he remembers to do the hydration checks. Anonymous has asked, when I compare coefficients, do I mean to compare inverse coefficients? No, it's easier than that. I just want to compare coefficients on each side of this equation. That was the previous part. I think I said multiply it up first to make it easier to look at the coefficients of where they are. I'm happier about comparing coefficients of positive powers of x, but I suppose it doesn't really matter. No, hang on, I do want to multiply it up so that I can recognise the left-hand side as the original polynomial. Yeah, multiply up the left-hand side, recognise that afterwards, after multiplying it up by x to the n as the original polynomial, write out what their original polynomial was in terms of the coefficients. The right-hand side, meanwhile, has done some tricks. The right-hand side is where the magic's happening. Where do we set a max? Yeah, hang on. How did you get n equals 50/50 from k equals 100? Because the very, very fast part of the question was to work out n, the degree, in terms of k. This question all knits together. It's all interlinked. Every part is there for a reason. The first part is to get this link between the degree and k. The second part is to do this inequality that we need later on. This is sort of a lie. Part 4 is unrelated to the other parts. But hey, 3 is also unrelated. Okay, not every part of this knits together. 3 and 4 are just also here. Good stuff. Okay. That's question 2. Questions about questions. Oh, why did we set a max to n plus 1? I don't think I did. I think I said a max is really big. It's bigger than or equal to 2 to the k over n plus 1. It's true from part 2. I said over here, the number of coefficients, different concept, not a max. The number of coefficients is n plus 1. We would need, if all of the numbers appear in all of those coefficients, we would need at least as many coefficients as we have numbers. So we would need lots of coefficients. We need more coefficients than we have different things we would like to see, so that we've got space to put them all. We would need n plus 1 to be bigger than 2 to the k over n plus 1. Because it would need to be bigger than a max. And that rearranges to look like this, but that's just not true for large values of k. Okay. Groovy. This question was also quite tough. I can't remember what the average score was on this question, but this last part people found it very difficult, I think. 2019 overall, I can't remember, the average score was about 43 maybe? Something like that for math students, which,
yeah,
gosh.
You put me on a lot of pressure with part 5.
Yeah,
Didn't
sorry.
like it.
The exponential polynomial comparison is not quite, it's quite hard. You can plug in values of k at the end there. Still, it's guessing that. I did really put you on the spot for that bit. Okay. Let's play. Oh, please explain question 3 again, or part 3. Yeah, part 3 is really weird. Part 3, I would advise you, if you really want to understand what's going on, explicitly work out this thing by multiplying out the brackets from left to right. So just P3. Just P3. And have a look for me, while you're working out P3, think about the x squared coefficient. So when you're working out the x squared coefficient of P3, you multiply the first brackets out and you get some quadratic, fine. Or you get some cubic, sorry, when you multiply the first brackets. And then you multiply that cubic by 1 plus x cubed. Homework to check you understand part 3 is to work out that cubic and then multiply it afterwards, then multiply it by 1 plus x cubed, and you should find that the x squared coefficient didn't change when you did that multiplication. 44.9, okay, slightly better than I thought. Okay, I'm going to go back to the poll. I'm going to see what the poll thinks we should do next. No, not that one, that's how you're taking part. And also, I want to switch on what next. I'm going to try and accelerate again, because I'd like to get through a couple more questions. Depends if they're short or long questions. I should probably take question 2 out of the poll. Daisy, would you like to stay for another one, or do you need to go?
I'll stay for another one.
Stay for another one? Okay. You're allowed to wait and see what it's going to be, if you like. I think it's very bright.
It's not 3 or 4.
I guess you should be glad it's the 2019 paper and not the 2020 paper, which is your actual test paper, and then thus, perhaps.
I wouldn't want to look at that again.
Right. People are still voting for question 2. Let me try and take question 2 out of the poll, so it's easier for me to look at. You know what? I think they're voting for 6 at the moment, or maybe it was people who were here before. Bop. Oh, come on slightly. There we go. I've removed question 2. A real professional would go remove question 5 as well, since we've done that one as well. Question an hour feels about right. 6 is doing really well, and 3 is doing all right as well. Oh, 1J. Was 1J one of mine? I can't remember. Could easily have been one of mine. Let's have an overview of 6, which in the pre-live, I think, before we went live, I think, Daisy, did you say your personal statement involved something a bit like this?
Yeah, because I was thinking about something to do with computer science. I won't go into too much detail about it, but I was just trying to make the way you could, or just like how you could number an order in like the most efficient way possible. And I came up with something like this, and I just thought that was a really cool thing I'll talk about in my personal statement. And then I found it as a question.
Yeah,
and
okay.
So yeah.
Let's do the overview of this question, because if we get bogged down in the details, then it will go too detail-y. And there is a video of, it's about 2 hours long, but it's me going through the the solutions in more detail than the work solution on the website. So if you're on the MAT page, you can download a web solution, which is a PDF of the solutions for this. Or if you like, you can watch a video of me doing the question in a little bit more detail than the web solution. I saw someone earlier, quite a lot earlier, ask for a more detailed mark scheme or something like that. A bit late for part 3 of question 2, sorry. Part 3 of question 2 was it eventually becomes constant. Multiply out the first 3 brackets and see what happens. Flexadecimal. There is a lot of reading at the front of this question. What it's trying to describe is a system where the maximum number you're allowed to have in each place. In binary, that's just 0 or 1. The maximum is 1. In decimal, the maximum you're allowed is 9. Here, the maximum depends on the position, which is a bit of a funny idea, to be honest. So this last digit is only allowed to be 1 or 0, and then the next digit is allowed to be I suppose a 0 or a 1 or then a 2, but it's not allowed to be as big as 3. Okay. And the whole question is about understanding what that means. How often do you overflow into the next one up? Daisy, what's your take?
Okay, so this is just a lot of factorials. So the way I think about this is that if you think of just like ones, if you just think like your units, your tens, your hundreds that you get in decimal, but here instead you've got your 2 factorials, your 3 factorials, your 4 factorials, your 5 factorials, and then in each column you can go to 1, you can go up to 1 less than the factorial that you're looking at. Like you can go up to 0, or you can go up to 1, 2, and then you can go 1, 2, 3 for 3 factorial. So when we're trying to when we get later on and we're trying to convert these, I think these factorial, like instead of tens and hundreds, these like 2 factorials, 3 factorials, I think they're going to be really helpful. So I think just for the first part, where we're just adding them one by one, I don't think that's not too hard to think about, but I think later on that becomes, like for part 2 and 3, becomes more important. And then I think towards the end of the question is where we're now thinking of applying it into a real situation, and we're relating it to arrangements, how many ways we can order things. So we're just thinking, and what you realize is that because we can have say 5 in the first column, then that relates to having 5 options, but then as soon as you take one out, you've only got 4 options left. So we've got a direct link between this and ways you can order elements. So we've got a couple of ways we can look at that. We can look at it in terms of decimal, or we can just look at it in terms of itself, and we can just see there's an instant connection there.
Brill. For me, I think the light bulb moment for this is when you're working out the numbers in part 1 and you get as far as 6, because you overflow into a new digit. 6 is written like this in flexadecimal. I followed all the rules on the screen. I was working it out while Daisy was talking. So they give me 1, 2, 3, 4, and then for 5 I'm allowed to increase the units digit by 1, but then for 6 I'm not allowed to write a 2 in the units digit. Well, that would be too big, so I move to the left, and then I'm not allowed to write a 3 here, so I carry the 1 over again, and I write it down 100. Or I write it down 100 in flex decimal, I guess. It's not 100, it's 6. For me, the light bulb moment is that's gone into the next digit at 6. The place value of that thing looks like it's 6. 6 is a weird number. Where have I seen 6 before? This is 2, this is 6. If I've seen a sequence with 2 and 6 in, I guess I have. That's factorials, I suppose. Or maybe they even make sense that you get the light bulb by thinking about how long until it overflows into the next one. And then you see this is allowed to be, this pattern is going to repeat, and this is allowed to just go up as a counter until it hits 3, until it wants to be 4. And it wants to be 4 when they hit 24. So spotting this kind of link, and you've got these ways in by working out those small numbers at the start to spot that, oh, the place values are just factorials. Once you've had that idea, I think that's the light bulb that then lets you interact with the conversion between decimal and flex decimal, and it lets you have this link between shuffling, permutations, which is all about factorials. Really is. If you've got some thinking about all of these factorials for the shuffles, that's closely related to these factorials for the place values in flex decimal. I like the way that this question doesn't tell you that place value is factorials.
Yeah, I think I did jump ahead a bit there.
Well, no, so you I guess went through the. Once you've seen it, it's hard to unsee it. It's hard to imagine what it was like before you realised that it was factorials.
Yeah,
all
and
along.
I think because when I first did this question, of course I already knew that.
Right,
so,
you had some previous experience, I guess, with things where it overflows in a strange way or goes into the next column in a strange way. For the rest of us, we've got to read. It's that second paragraph we've got to read to work out what the rule is for going into the next digit. So that's really how I would demonstrate by converting my procedure. They've phrased this to really not give the game away, but I would convert it by writing out 1 times 24 plus 2 times 6 plus 2 times 2 plus 1, because I've worked out that it's a place value system and the place values are factorials. And then convert them the other way by, I think a greedy algorithm works, and adding them by just doing some careful overflow stuff around here. And it's not, once you've worked out what the rule kind of is for how place value works, it's much easier. I absolutely adore the way that they have written this here, because maybe I've overstated that, but they could have written 6 factorial here. They could have written 720 in decimal, but no, they've written 1,000,000 flexadecimal number for how many ways there are, which is a bit of a clue that the arrangement, something you know about with factorials, is closely linked to the numbers that look nice in flexadecimal. This question's got something fun going on. Okay, chat's gone a little bit quiet. I don't know, maybe this. Everyone appreciating question 6. I propose some sort of rapid fire 20 minutes bit at the end to try and go through other things that people wanted. You might have noticed that when I've got a guest on the stream, I'm much better behaved. I'm focusing on a whole question. We're going through very carefully, and I thought 20 minutes at the end here of just the everywhere all at once approach, just to see. There's a request in chat to go back to question 2 and talk about part 3 again, or was it part? Yeah, one of the parts in question 2 again. So I just want to point to this one more time. Normally, when you have these polynomials, we talked about these before, indexed by k down here, they could be horrible. That's just a sequence of polynomials. Really horrible topic, loads of stuff it could be. We actually understand, because they've given this definition, we've understood pretty much what the relationship between these polynomials is. Some sort of, if you like, some sort of recursion relation, or some sort of relationship between one polynomial and the previous one that looks a bit like pkx. Oh my goodness, come on, pen, you can write. We're in quick fire mode, pen. We're in quick fire mode. The pen is not in quick fire mode. It's 1 plus x to the k multiplied by the previous one. That would have been easier to say out loud. Okay. A previous polynomial multiplied by 1 plus escape. That's not a bad relationship, really. It could have been much worse. Okay, over to 1F because we're getting requests from chat. Yes, this is a trigonometry question. We did an episode on trigonometry, a little bit classic. Daisy, when you see a combination of sine to the cubes and cos squareds in one of these how many solutions questions, what do you try?
Okay, well, firstly, we want to make all the sines and coses the same thing.
That's a good idea,
Yeah. So with cos squared x, yeah, it's just 1 minus sine squared x. And now we can just do a substitution for sine x. And then we've got a horrible cubic we've got to think about.
We're going to be careful when we do a substitution like this, I suppose. I can't remember the answer to this question, so this is pretty high stakes. Come on, we can do it. We can do it, everyone. We've got to remember this means that just naturally, as a result of this definition, I guess really because x is a real number. Stop the clock. I mentioned real numbers and complex numbers. But because x is a real number, u is between -1 and 1. That kind of restriction just exists because u is sine of x. I've done the wrong part of question 2. Sorry, that person. U is between -1 and 1, so I need to worry about that a little bit. Can I spot any solutions to this? No, I cannot. Can I think about how many solutions this has? I sort of want to rearrange it, I think. What do you think at home? Number of solutions to a cubic is a little bit of a tricky topic, I suppose. I've tried to rearrange it a little bit to be u squared 1 minus u, which looks like this. Question being, how many solutions are there where that's equal to 1? Oh. I wanted to rearrange it like that because I thought it'd be easier to write, but I'm not totally convinced it was. So the solution over here on the left, let's try plugging in -1 to this cubic that we've got. -1 in the cubic gives me the value of 2. So at -1, the value is 2. That's good news. That means there's a solution somewhere in here for a negative value of u. And over here, what's the maximum of this quadratic cubic? Daisy, I'm going to calculate. Can you try and explain what I'm doing? Sorry, this is a bit throw you in the deep end. What am I doing? You explain, I'll calculate.
So I think now we're trying to find whether so we can see that we're trying to find where this cubic, where the turning point of it, where this turning point in this cubic is, because so we know that 1 goes through the origin. But you need to find this other one, and we need to find how high it goes to see whether we're intersecting with this line or not.
I think the turning point is at 2/3, comma, 4/27.
So it doesn't go over that line. And
Brilliant,
you don't have to
yeah.
work at it.
So I think I've just got a negative value of u that matches up. Yeah, JWC, I agree with you. Differentiate and find where the turning points are. That's also a great explanation of what I was doing. But due to chat lag, I think JWC may have said it before I started doing it. Find the turning points. Yeah, good. I think there's no more solution over here. So just one negative value of u. Negative's kind of irrelevant, but hey. But that's the value of u. The pen, come on. Value. Quickfire. 1 negative value of u, but that corresponds to, I suppose, 2 values of x.
Yes, be careful.
Be careful, always. This is also a result of this change of variables, or this substitution that we did to talk about whether this thing's going on. Find out whether it's increasing or decreasing, determine if x is greater than or less than 0. Yep, sounds good. I had to check this -1 as well. I was worried that at this point, I could tell it existed, because this light blue cubic is going to shoot off to infinity over on this side. But I was a bit worried if it would get there in time, because I know that u is bigger than -1, so I was checking does that intersection with this line happen before or after it gets to -1? Excuse me, a little bit clumsy. I think my answer is C. Somebody check it. Chat, over to you. Is it C? Pretty sure it's C. While chat's looking that up to check, is it 2? I think it's 2. Feels like 2. Feels like it's either 2 or 6. So, and 6 wasn't one of the options. While we're doing, because I'm lovely, I'm going to go back to part 4, which I didn't quite finish off. So part 4, on the right, I've written out what happened when we substituted 1 over x into the original statement. My big plan is to multiply out by x to the n. That has 2 effects. When I multiply it by x to the n on the right, I get a polynomial with the coefficients listed one way, but the powers of x going the other way, which is a bit funny. And on the left, I might have mixed up my right and left here. On my left, I get this bracket. I can take that x to the n. Oh, come on. I can take that x to the n, and I can split up the x to the n into an x to multiply the first bracket by, an x squared to multiply the second bracket by, all the way up to an x to the k to multiply this last bracket by. I'm allowed to do that because x to the n is equal to x times x squared times x cubed times blah times x to the n by part 1. This thing on the left is exactly the original polynomial. I know its coefficients. I know its coefficients from the first definition. On the right, I've got this weird backwards thing. The way those equate says forwards polynomial is equal to backwards polynomial. Good. The answer is C. Thank you, Pi, and thank you, Jack. Hopefully we had something like a correct method for that as well. I saw a vote for 1J as well. 1J is one of mine.
Oh no. I remember 1J, it was awful.
It is not very speed round of me. Have I done the story for this one? Have I done the backstory? Oh, it's one of mine.
I want to hear it myself.
Was that you want to hear it or you don't?
Yeah, I want to hear this.
So, I wrote this question while cycling home. In a way, I was cycling and I was appreciating the fact that my front wheel of my bike was a circle and not a triangle, because triangles aren't round. If it was a triangle, then as the wheel rotated, sometimes it would be a nice tall wheel and sometimes it'd be a narrow, sometimes it'd be a wide wheel, from the point of view of where the road is and where my wheel is. And that more or less, there's a little bit of a modification to turn that into an actual problem, but more or less that's what's going on. We've got a triangle and we're spinning a line, which turns out that was easier to write down than having a line and spinning the triangle. But yeah, cool. So we've got an equilateral triangle and we're sending a line through it. The line might be like this, whoosh, through the middle, or it might be through that corner, or it might be halfway in between, or somewhere else. This question's probably too hard. Sorry, everyone. I quite like J because it's the first letter of my name, so I quite like writing 1Js. This one is probably maybe even too hard for a 1J. The way I think about it is to imagine changing the angle of the line. Imagine rotating the line, because I'm still thinking about my bike. I'm thinking about rotating the triangle, but imagine rotating the line and imagine the function for how wide is this line PQ, which is here, and then sometimes it's here, as that spins around. To imagine that function. Now the function is symmetric as you go forwards or backwards. So let's start from 0 angle as this line. The function's symmetric as you go forwards and backwards, and it also has it's periodic, because when you get round to 360 degrees you've spun the line all the way around, and in fact it repeats when you get to 180 degrees, because at that point the line's the same, so you get the same bit over here, and in fact it's the same when you spin this line around 120 degrees, because then you get from one corner, you've spun the line around to the other line. And in fact it's the same when x is 60 degrees, because if you spin the line 60 degrees, you get back to a point where instead of the line going through that point, the line's now going through the midpoint and the top of the triangle. So this function is basically constant. That's not quite true, of course, it's not constant. But it's constant every 60 degrees. So you've got to think about what's going on in between this 60 degrees. And we've got this value for whatever it is at 0, which is also the value at 60 degrees. And is also the value at minus 60 degrees, I suppose, if you start spinning it the other way. And in between, It's nice and symmetric, and it's symmetric under translation as well. The graph is symmetric under translation. Those things paired together mean that it has a symmetry around the line 30 degrees. It's symmetric because you can translate it and you can flip it and you can flip. It's just a lovely graph. It's going to be something like a sine graph, but not quite. That means that it goes down and up again in between. And then it's kind of obvious to me that it has a maximum at one of these. Either it has a maximum of 0 or it has a maximum of 30 degrees, but it oscillates between. Because it's so nice and symmetric, it can't have a turning point somewhere else. This is not quite a rigorous proof, but it's one of the multiple choice questions. So this is okay. Still got to do the actual maths to work out at 30 degrees. At 30 degrees, when the line is parallel to one of the sides, but doesn't go through any of the corners. 30 degrees. We've still got to do some maths to work out what the answer is for how long that line is. How do you find the minimums between 0 and 16, not the maximum? You could check both of them. I think if you work out one of them, it's 2/3, and if you work out the other one, the value is root 3 over 2, and 2/3 is smaller than root 3 over 2. So if in doubt, work out the value at 0 and the value at 30 degrees. Speed round. Not very speedy. Yeah, something about Rayleigh triangles. I was trying to think about it because I was trying to think about Rayleigh triangles. I think that's not how Rayleigh triangles work. Maybe it is how Rayleigh triangles work. Daisy, do you know about Rayleigh triangles?
No.
Sorry, I really took over that question with my bicycle story and then my rambling through breakneck speed.
I'm glad because I don't like that question.
No, sorry, nobody likes that question. One person in chat says this was my favourite. Maybe it's a delayed chat message though. They were talking about something else. We're running out of time a little bit. It was in a Sums magazine. I submitted my answer and it got featured in the following edition. Yeah, Sums magazine asked me if they could use it, and I said yes because I wanted more people to see it. More people to. This was my favourite question. It's one of mine. It's the right. This is not very original. I've seen it in other places as well, but it's a combination of. It's a mashup question. Geometric progression mashed up with right-angled triangles. Do both, and it turns out to involve the golden ratio, which is always nice. How do you find the length once you've identified the angle? Now it's a kind of straight up. So Jay, once you've found the angle, you have the kind of straight up geometry question of here's a line parallel to one of the sides, going through the centre, whatever that means. How long is the line segment? You need to work out where the centre is of the triangle, which is not impossible, but is a little bit too hard. It turns out it's 2/3 of the way down, so the length of the side is 2/3 as long. I think there's a similar triangles thing you can do, but gosh, do some trigonometry. Drop some perpendiculars or something. I'm not being very helpful, sorry. Drop some perpendiculars, do some trigonometry. Ugh, bit of a mess. It's not a nice question. Even once you've worked out what's going on, it's not nice. What else do I like? Is this the one with the eye that nobody got right? No, this is not the one with the eye that nobody got right. That's coming on next time. They roll but the centre moves vertically. Is this question secretly just an equilateral triangle is not a Rayleigh triangle? I think that might be it. Anyway, might be what's going on with this one. Any of these any good? I think I know what that is from the shape of it. Sorry, the question's gone very blurry. It's the cubic, roots of a cubic thing. Similar ideas for a different one. Okay. Having a quick look at the poll, so we've got 7 minutes. Daisy, while I've been scrolling around, have you seen anything that you enjoyed doing from this past paper question?
I didn't enjoy it, but I like the look of part G. It doesn't look enjoyable, but it looks interesting.
Like the look of 1G? Or was that my triangle question? Or was that... Oh no, that's not my triangle.
I think the triangle is...
Oh yeah, it's one of these logarithms. How many solutions? The trick, as always with these sort of questions, is to turn it into a system of equations and then try and solve the equations. And solving a system of these, they tend to be like nice polynomials once you've rearranged quite a lot. Solving simultaneous polynomials is something you have a bit of experience of from school, and you can do tricks like sketching graphs to work out how many solutions there are. Loads of votes for question 3, which I actually can't find. Not joking, can't find it. Is it over here on the left? Sorry, I'm getting a lot of lag as well. Question 3 is not too bad, right? Question 3 is not too bad. Okay, so it's got a lot of votes. Question 6 has also got a lot of votes, which is unfortunate because we just talked about it. Question 3's got lots of votes. Do the integral is fine. Explain what this is. You will need to understand that this graph is a translation. This graph is a translation of this one. Daisy, did you have to? No, you didn't have to do this question because computer science, right?
No.
Okay.
So I might have had a very brief look at it, but I don't remember it.
I don't know how helpful I can be about this question with 7 minutes and a pen that doesn't work. How helpful can I be with 7 minutes and just talking out loud? The first couple of parts are pretty standard. I think you do some integration fine. Without further calculation is brilliant because it means don't overthink it. Just say why it's this. Do some argument about it being a translation or something. There's some solving some simultaneous equations. Meeting tangentially means that there's a repeated root when you look at the equation for the difference between those two curves. There's a repeated root. Two curves, the line and the curve. Look at the difference between them. There's a repeated root. That's something that we had. I think people are not very familiar with that as a technique, as a thing. So there are other ways to do this, about like writing down a quadratic or something. But here's one way that does involve writing down a quadratic. I had long enough there to forget that my pen's not working. This quadratic, for setting these things equal to each other, should have a repeated root. Or said differently, the difference between them should have a repeated 0. Okay. Question 6 has won that vote, which is a bit funny. 1H is doing quite well as well. We might look at 1H in 3 minutes. So we do some calculation at this point, I think. We've got this expression for the area of the region S, and we know the value of M. Given that the area of R equals, okay, so we're given the area of R, and we want to say that they're equal. Well, that means writing down the area of S. We know the area of S in terms of B and A. We've been given numbers now, so this is beta squared minus 1 in code. Replace the b's with beta squareds, replace the a's with 1s. Write that down, set it equal to this expression for R, do some rearranging. There's quite a lot of messy rearranging. Beta squared minus 1 should be ringing alarm bells for difference of two squares. Yeah, rearrange it. Explain why the solution is just that kind of graph method again, to think about the graph of this function, to think about how after b equals 1, this thing is positive and getting large, and this thing on the right hand side is also oh goodness, what is that doing? After b equals 1. No, goodness knows. I've confused myself. Is this thing, this term inside brackets is maybe changing sign or something like that? Goodness me. Yeah, as it's sort of, this bit's positive, this when beta equals 1, this thing is negative. So overall this turns negative. Daisy, someone in chat says, what do you enjoy making notes on at university? More paper or more digital?
Well, I think I definitely prefer like making paper notes. I think I find that much more helpful. But also, I think I do a bit of both, because paper notes is also very hard to organise and very easy to lose. But I think paper also, I just find paper easier, to be honest. But I've never really gotten into like things like latex and stuff to make really nice notes digitally. So I think I'm just paper personally.
LaTeX is a bit of a pain to work with. It's a bit of an acquired skill. LaTeX is what this maths is written in. It's the difference between this just being in Microsoft Word versus being nice. The very last part of this question is maybe too hard. I've been reading it while Daisy's explaining notes. The information that we've just worked out, that there is a solution where the areas are equal, in this particular case when A is 1 and B is positive and bigger. So B is positive and bigger than 1, A is 1, A is on the left, B is somewhere bigger. In that case, we've proved that there is some value of beta. you can choose that value of beta so that the areas match up. That is supposed to be enough information to deduce the general case that if A is not equal to 1 but it's something else. The idea is supposed to be that you can take that picture, this kind of imaginary picture that we've just got where R and S are the same size, and you can rescale everything. You can kind of drag everything bigger, and if you scale everything properly, then R and S stay the same size, but you can get to other values of A and B. So if you take the picture where R and S are the same area, the picture on screen doesn't look great because R and S are obviously not the same area in the picture. But if you imagine they were, then you could take that and you could photocopy it and you could blow it up large, or enlarge it, or stretch it, and they would stay equal area. That's supposed to be the idea for the last part. It's slightly fiddly to actually write down the details. It's maybe a little bit too hard. But yeah. Is the equation editor in Word just LaTeX? I think it's not, but I'm not sure. Maybe it is now using some sort of LaTeX MathJax thing to implement stuff, but LaTeX comes with a whole set of rules about laying out pages as well that Word's equation editor doesn't do. LaTeX is completely overwhelming to learn. Right, okay, we've hit 7 o'clock, so at least I'm going to let Daisy go. Thank you very much for joining in, Daisy. Thank you, Prisma, for moderating the chat as well. Thanks everyone for coming. I'm going to have a sneaky look at 1G and 1H because somebody asked for those. Maybe, if my tech plays along. But thank you very much, Daisy, for joining the live stream.
Right, thank you.
I will see you round. I'm going to hang out for another couple of minutes just to look at some other questions.
Okay, goodbye.
Bye.
Yeah, bye.
Everyone says bye in chat. Okay, 1G, 1H. 1G's loads of work though. 1H is brilliant. Just draw your triangle geometric series in H. Give the sides names and you're fine. 1G, I haven't done this question for a while. The video solution is quite good, if I say so myself. The idea is to turn these into different equations, right? So doing the only thing I can, which is to get rid of these logarithms. I remember in the logarithms episode, the answer was always get rid of the logarithms, which is a bit sad for someone who's a fan of logarithms. These equations look absolutely horrible. They've got variables in the powers, which vaguely terrifies me, to be honest. But I think I can deal with it. Have I done them all correctly? Yep, I think I have. I think I can deal with it by noticing, gosh, that I can plug in this b, this expression for b. These first two are just kind of b's and a's. They kind of relate to each other. I can plug this one into that one. A to the c to the power of c plus 3 over 2. That's a bit weird. That's a good starting point, I think. On the left, I've plugged in b. On the left, I've got a, which is just a to the 1, and then on the right, I've got a to the c plus 3 over 2. That's pretty good. I think that tells me that either c times c plus 3 over 2 is equal to 1, or something weird is going on with a. So, goodness. Yeah, somebody's found the mark scheme bit. We should also stretch parallel to the y-axis to make sure that the leading coefficient of the parabola is still -1, but candidates were not expected to spot this. The stretching argument is actually really subtle. Good, okay. I feel like I'm getting close to solving for the value of c. So I can have two possibilities for c, and then I'll take those and I'll take that number. I think it turns out to be either 2 or 1/2 or something like that, and I'll plug those in so that now I've got an expression over here that relates a and b together once I've worked out what c is, and over here I've got an equation that relates a and b together once I know what c is, and probably I plug those into each other and I get some expression that's just in one variable. And I try and think about how many solutions it's got. And that's really what we're doing. We're trying to eliminate variables and get down. So first I'm eliminating b by plugging this into the middle one, and then I'm trying to solve for c, and amazingly I can solve for c. Not guaranteed that you can solve this sort of thing when you've got like 2 letters inside some horrible expression like this, that you can solve it at all, but that's what I'm going to do. And then hopefully follow through from there. If you like, the video solution afterwards will also be a way to find out about how that calculation actually works. Morally, bash them together, try and work out how to bash them together, try and work out how many solutions there are. The bash them together, I've just realised, is the rude gesture that Ross invents in Friends. So sorry for doing that one to everyone. Okay, on that note, I think I'm going to call it there. Other 2019 solutions are available. on this YouTube channel on the MAT 2019 video and in Web Solutions. Thanks to Prisma and Daisy who were here to help out with this live stream. Once again, I don't know how to stop. No, we can work it out. I will see you again next week for MAT 2020, which was a bit easier than MAT 2019, I think, based on the average scores. Getting there and trying some 2020 questions next week. I'll see you then. Take care, have a good week. Bye.